So this is part 2 of the video series at this point, taking us into electromagnetism beyond what is expected for you that you understand in Physics 162. Right, so I hope you had your coffee refill or your wine refill. I hope you got another scoop of ice cream, whatever it is that you're doing while you're watching this. I hope you're having a good time. So here's where we left off. Right, we wrote down Maxwell's equations that we now all fully understand, including a little completion to it that we didn't have previously, that we called the displacement current. In a sense, those laws tell us all there is to know about electromagnetism. Everything else follows from those laws. Everything else is applications. Now, of course, it would have been a terrible course had I just given you those and said that's all you need to know. Right? You wouldn't have learned very much at all. So we human beings don't learn it that way, but now that we've kind of built up the edifice that is electromagnetism, we can say these are the 4 pillars of electromagnetism. The so-called Maxwell's equations, each of which has its own name. Right? This one's called the Ampere-Maxwell law, like I said it before. But Gauss's law, the other Gauss's law, Faraday's law, and so on. The one thing I could add here to this list is the Lorentz force law. You know, this little thing that said the force on a particle is the charge of it times the electric field. Add to that the effect of the magnetic field. But this is sort of a separate one in that it tells us about what charges do when you have fields, right? So in a way we need this, but these ones, those 4 are what are called Maxwell's equations. They describe how fields affect each other. So we talked about this asymmetry, that there are electric charges but no magnetic charges, and therefore electric currents but no magnetic currents, right? There's no extra term here. So this term is like this one, but this one doesn't exist up here. But now let's throw out the electric charges too. So now let's go to a vacuum. So we're going to worry about Maxwell's equations in vacuum. Now you might say in vacuum, wait, if there are no charges there at all, no currents, nothing, like, is there anything? Well, let's see what the physics says. So we're going to write down the equations again, but we're going to pretend there are no electric or magnetic charges. There are no electric charges, we know that. Sorry, there are no magnetic charges, we know that. But now we pretend we're out in space somewhere far away from all charges. So what is that going to do to our equations? So this thing is going to be 0. And this thing is going to be 0. Because there are no charges, it could be enclosed to any surface, because there just are no charges. And there are no currents, because currents are made up of electric charges that are moving. And if there's nothing there to move, well, then you can't have a current. Let's write down those laws again. So first I'm going to write Gauss's law. And Gauss's law is now going to say, of a closed area, closed surface, it's called S, E dot dl. Sorry, what am I doing? E dot dA, area dA, it's Gauss's law, is equal to 0. I'm going to get the Gauss's law for magnetism. Let me write this here. Surface integral over a magnetic field. For a magnetic field, the magnetic flux is also 0. I'm gonna get that for a loop L, this is a line integral. That is not 0. That is equal to the negative of the rate of change of magnetic flux, whereas the line integral for a magnetic field, well, that's Ampere's law, right? And Ampere's law says you've got this one, but this one is 0 now because we're out in space where there are no currents. So we're just left with this, the rate of change of electric flux. and those constants included here rather than here, essentially due to, if you like, a historical accident, the way they're defined. So we're not going to be mathematically rigorous here because it would just, require a bunch of multivariable calculus and a bunch of theorems and so on to actually make sense of all of this. The key insights, right, that we kind of already stated are here. And they are: changing magnetic fields cause electric fields, changing electric fields cause magnetic fields. Changing E causes B, and changing B causes E. Alright, that's exciting. Now, so if you look at this carefully, you might say, hold on a minute. There are no currents out there in space, there are no charges, so it seems like all the fields should just be zero. But you look at those two statements and you say, wait a minute, is it possible that I could have an electric field that's constantly changing, and by constantly changing it's creating a magnetic field in such a way that that magnetic field is constantly changing, and by constantly changing it creates the electric field in the first place, kind of this circular dependence, right? So let's ask like this: can we look at those and we ask, can E and B keep each other going by changing constantly? Of course, mathematically, and maybe in some particular way. Let's write in the right way. And the answer is going to be yes. I'm not going to prove this because the math is sort of a bit involved. I refer to section 31.5 in the book, which sort of does the math. It fudges a few points, but it kind of gets there. It just fudges points because where you need a bit more advanced calculus in a way. So I'm going to say C 31.5 for the math, for most of the math. So let me just very briefly do something just so you've seen it. So you can actually rewrite those laws by applying what's called the divergence theorem and Stokes' theorem. And those are things that I'm not going to explain now, but they really, what we might imagine doing, just conceptually, is like this is over a closed surface, right? Kind of like a sphere, a cylinder, whatever, this integral. Now what happens if I imagine a little ball over which I work this out, and I make this ball infinitesimally small? What does that lead to mathematically? Same thing here. Now with this one I have to have a loop, right? This has a little loop, I do a line integral around. Well, what happens when I make this loop infinitesimally small? So I make it shrink down essentially to zero. What does this equation get me? Here's what it gets you. You can rewrite Maxwell's equations in a different form. In what's called differential form. The other form up here was called the integral form. But strictly speaking, this is the integral form, right? This one here is the form in vacuum. In differential form, and I'm just worrying now about in vacuum. You can also find a differential form when they're not in vacuum, when there are charges, charge densities. But you can take another electromagnetism course for that, or look it up. So those laws, Gauss's law, essentially becomes what we call the divergence of the electric field is zero because we're in vacuum. If it wasn't vacuum, I'd put the charge density over epsilon naught over here. the magnetic field gives me the same thing. The divergence is 0. So if you don't know what this mathematically is, because you haven't taken vector calculus yet, don't worry about it. I'm just including it for completeness. And then the other laws become what we call the curl. The curl of the electric field is the rate of change of the magnetic field, and the curl of the magnetic field is epsilon naught mu naught times the rate of change of the electric field. You can sort of see how these ones look a little bit like those, where flux has become just field, like I've divided again by the area, and somehow this line integral has become this grad, which we met, and grad cross product with electric field. If this means something to you, great, right? Then you can fill in the gaps maybe. Maybe you can apply the divergence theorem and Stokes' theorem to those equations and figure those out yourself. If not, it's essentially a sort of way to write down Maxwell's equations, but applied to, I imagine that the closed surface of my integral and the loop essentially become infinitesimally small, right? That'll lead to those in vacuum. So what you can do then is you can essentially do some algebraic manipulation, essentially plugging what you know here for E into here. No, actually, what you know here for E, you plug into here. Since you take the curl of this whole equation on both sides, and I use this, and what you end up with after using some vector calculus identities, which you know if you've taken, I don't know what calc course it is, vector calc 1 or something, you end up with an equation. Let's right now do some vector calc. It's actually not that hard, but this is not the time and place to introduce you to vector calculus. And simple algebra. And what do you end up with? Let me see if I can focus this a bit more. What do you end up with if you do that? You end up with essentially one equation, two equations. You end up with an equation that looks like this. The second derivative of the electric field with respect to time is equal to 1 over mu naught epsilon naught times the second derivative of the electric field with respect, this is a t, with respect to position, let's say x. That's the second derivative, right? Maybe you can fill in the steps, maybe you can look them up, maybe you don't care, that's fine too, right? That's fine too. Just want to try to get the idea here. So I've used Maxwell's equation and did a little bit of mathematical manipulation to it. I didn't make any new assumptions or anything. There are a few details here, a few insights we're going to skip, but this is what you get. This is what we call a wave equation. So what is it? What is this telling us? It's saying that, look, the electric field in vacuum, whatever it is, could be some function. Whatever function of position and time it is, it has to satisfy this equation. This is a differential equation. So-called partial differential equation, which again is something you learn about when you take a differential equations course, which I hereby command that you do, because it's useful. So you can ask what function E of position and time satisfies this. What sort of function E as a function of time, space and time, makes this true? Everywhere, so at all x, and every when for all t. Right? Because the laws of physics apply everywhere and every when. So electric field better makes it true. Now here's the answer. I'm just going to give you the answer. Again, you can check that it is true. Let's say the electric field, at least one of the component, let's say the y component, They say I've skipped a few bits here, especially about directions, because we just care about the basic idea. Is some constant, I'm going to call it E naught, times the sine of kx minus omega t, where those two are really just constants. There, you can sort of, this you can check that this is a solution to this, provided omega over k is equal to 1 over mu naught epsilon naught. Oh, sorry, this squared. You can check. So here's what you do. You take this expression, you take the second derivative with respect to x, you take the second derivative with respect to time, and you should find that this equation up here becomes true. Obviously, left hand side equals right hand side, provided those two together, this fraction here, is equal to this. Now, if you've taken a course on waves yet, you recognize all of this stuff as, you know, being the kind of equation that allows for wave motion. But if you're doing 163 next, you'd see it there, right? If this is, you're taking 162 right now, which I assume you are because you're watching this video. So you'd learn meet this equation again, maybe with not e's up here and maybe other constant, but this form of equation again in 163. So what does this look like? Well, it has two variables, so I can't really draw it, but imagine I fix time. I say at time equals 0. It's a sine function. Now, if I change my time, right, then it's gonna, what does it do? If you add or subtract a constant inside the sine function, it's gonna shift the function left and right. So what this looks like is this. So this is E as a function of time. Sorry, it's a function of, well, it could be time. Let's say space. At time equals 0, it looks like this. At time equals 1, it looks like this. Right? I'm just drawing this function for different times. Of course, 1, 2 word units doesn't matter. You get the idea, right? So the sine function, this wave, is shifting to the right. Or it could be to the left, right? Depends on the directions, doesn't matter. Could be in some other, not in the y direction. So notice though that the component of the electric field is like in the y direction, and this thing might be moving in the x direction. Again, I haven't proved it to you. We skipped a bunch of the math. The book goes through some of it. It skips a few things. But essentially what you can show is that the speed at which this function moves to the right is equal to omega over k, those omega and k, just based on how functions work, just how sine functions work. Pure math. And that we know is equal to this. So what is the point of all of this? Well, it's saying, look, Maxwell's equations in vacuum lead us to this. This says the laws of nature allow for electric fields to exist that oscillate like this even when there are no charges around. Now, if you do that, right, you say, okay, if I've got an electric field like this, you still have to satisfy Maxwell's equation, so you ask what happens to magnetic fields, and here's what you find. You find that if the electric field behaves like I've just shown you, see if I can draw this. We'll draw in 3D now. Right, 3 axes like this. Then the electric field might be doing something like this. The sine function. I'm trying to draw this in 3D. It's a bit hard. You get the idea, right? Point straight up, then point straight down. Straight up, straight down. So that is allowed by the laws of physics. Maxwell's equation says, hey, if there's this function of electric field is permitted by the laws of physics to exist even when there are no charges. But you plug that back into Maxwell's equation, this solution, and you ask, what's the magnetic field like? And you can do that yourself, I think, with the equations that I've given you. You can try this at home. You find that it only works out if the magnetic field at the same time does something like this. So you really have to think in 3D here. Okay, sort of like imagine this is essentially sideways, like in the other direction. But they get bigger and smaller together, so that what we say we call in phase. But this one goes up down, and the B field goes left right. Could be the other way around, of course. Depends on which direction you're looking. Could all be twisted. That's what we call the polarization. Which way is the B field? Which way is the E field? But you have to like twist the whole thing together. And this is what we call an electromagnetic wave. Right, it consists of an electric field and a magnetic field, and they're allowed to essentially keep each other going, right? Because changing electric field create magnetic fields, changing magnetic fields create electric fields. They keep each other alive, mathematically speaking. Right, you can't just have one, but the changing electric field causes the changing magnetic field, which causes the changing electric field. So that's why light is a thing, right? The Maxwell's equation in vacuum allow for exactly this sort of behavior to happen and not much else. Now, we said that the speed of this wave, right? That's the speed of the wave was equal to 1 over the square root of mu naught times epsilon naught. And you do the math, and you get that this is roughly 300 million meters per second, or 300,000 kilometers per second. That's what we call c, the speed of light. For some reason we use c rather than v. Again, it's just, v means speed of anything. C specifically usually means the speed of light. So it follows from the math, right? Maxwell's equation, after some algebra, understanding differential equations, and so on, leads us without fail to conclude that electromagnetic waves are possible in nature, and if they exist, they must move with a speed that's equal to this. Any other speed would violate the laws of physics. Would violate Maxwell's equations. Alright, so I'm going to come back to this in just a second. We're getting there. Let me just talk about a little bit about, what do these waves do? And why can we see them? Why can we detect them? So one example you might think of is an antenna. So let's say it'd be a little aside. Talk about antennas. What's an antenna? Antenna is a long piece of metal. Long piece of a conductor. So what happens inside the conductor? Well, imagine inside the conductor there are some charges, right? There's a positive and there's a negative charge. It's made up of atoms, right? Some free electrons especially that can move around. And now you apply to this, now the electromagnetic wave comes in. Let's just focus on the electric field. I've changed my color scheme now. I'm going to make this purple so I can use green for the electric field like I have before. So here's my wave coming in. Of course it doesn't really look like, it doesn't move in space up and down, right? It's coming along a line and along that line is an electric field and a magnetic field value, but I can't draw that. So this arrives, pushing the pluses up, the minuses down. A little bit later, this part of the wave arrives, pushing the minuses down, the pluses up. A little bit later, this part of the wave arrives, pushing the pluses back up, the minuses back down. So the incoming electromagnetic wave could be a light, could be a radio wave. It jiggles, this is the technical term obviously, jiggles electrons in the antenna. Now what does that do? Well, because the antenna is hooked up via some cable to a conductor, if the electrons get pushed down, they push down the electrons in the cable, and if they get pushed back up by the incoming wave, the electrons, they jiggle back and forth. What does that mean? It means you get a current that's forwards and backwards, sort of forwards, backwards, forwards, backwards, forwards, like they're jiggling forwards, jiggling backwards. And if this is jiggling, then the electrons on here are jiggling too. So you get essentially a tiny alternating current, meaning one direction, other direction, one direction, other direction, that's switching back and forth at a frequency that matches the frequency of the incoming wave. Now at this point, what do you do with that? Well, then you can hook some kind of complicated circuit to this that reacts to these jiggles, for example, by using inductors, which create natural sort of time dependence and are sensitive to certain frequencies of jiggles. Again, all down to understanding induction very well. You hook this up, and so you might be able to say if it's jiggling with different frequencies at the same time, because there's more than one wave coming in. You might be able to like separate those different jiggles out, and that allows you how to tune your radio. Actually, tuning a radio is a fairly simple circuit if you understand inductors and resistors. But whatever happens next, right? The point is that the circuit, through the current motion, is picking up the electromagnetic wave that's coming in. Like it's picking up the frequency, right? And that's ultimately how you can transmit information via an electromagnetic wave. You just jiggle the frequency of the wave in at a certain time. Like faster now, slower later, bigger, smaller. That'll get picked up by the jiggle in the current, which you can then analyze with the right type of circuit. Because another thing that these waves do, other than you can pick them up with antennas, they also transmit energy, because whether something over here far away caused this wave in the first place, maybe some charges moving over here, changing electric and magnetic fields, they move through space based on how Maxwell's laws apply to empty space, like what we talked about, and eventually they hit this antenna and they make the atoms in here jiggle. So somehow, or the electrons in here jiggle. So you had particles jiggling over here, causing particles over here to jiggle. So somehow you moved energy from over here to over here, right? Because jiggling is kinetic energy. So electromagnetic waves, like any other wave really, they carry energy with them. The details, well, I'm not going to worry about the details. The concept here is what's important. How much energy, as I say, take a more advanced course on electromagnetism, and you'll study all that. Or maybe if you're an engineer, you might be interested in like the signal processing. How do I disentangle the electron jiggles and turn them into, my favorite music that is playing at my local radio station? Different story, lots to cover before you can fully understand that, so take an appropriate course for that. I now just at the end want to come back to one little curious thing that kind of takes us full circle. So remember how I said the speed of light, the speed of those electromagnetic waves is 1 over mu naught epsilon naught, right? That's what Maxwell's laws say. But hold on a minute. In which reference frame does this apply? Right? The speed of something depends on your frame of reference. Right? Remember at the very beginning of part 1, the moving train? Right? So we had our train, here's a train, and there was our experimenter Alice walking along in the train. She was walking at 1 meter per second, the train was going 10 meters per second, so was she moving 1 meter per second or 11 meters per second? Well, it's a matter of perspective, right? We noticed back then already there's something funky going on with electric and magnetic fields. Now we seem to have this question, look, we've derived the speed of light in terms of those two values. But if there's a light wave going past the train at 300 million meters per second, does Alice, who's moving 10 meters per second, or the train driver who's sitting still, right, moving 10 meters per second to the right, do they see 299,990 meters per second? Because they're sort of keeping up a little bit with the light? No. Well, the only way this could be is if they changed the value of those constants, right? So is it the case that mu naught and epsilon naught have different values depending on whether you're moving or not? Again, it turns out the answer is no, right? You could, I guess you could sort of test it experimentally, probably fairly difficult to do. But no matter what reference frame you're in, you're doing some experiment on a train or out here, those values have the same, those constants have the same values. The attraction between two charges is going to be the same whether they're here, assuming everything else is the same. So the conclusion we come to is that the speed of light must be the same in all reference frames. That is utterly bizarre. It just does not make any sense, because surely if the light is going to the right, I'm moving to the right, it's moving slower relative to me. Turns out it doesn't. For the longest time, people were confused about this whole idea. They're saying, look, maybe there's some fundamental reference frame where things are addressed, like the ether. And they tried experiments to figure out, to measure the speed of light really, really accurately in different frames. For example, what you can do is you can build a certain, what's called an interferometer, where you essentially have different light, you shoot light in different directions, and you have it come back and interfere with each other. You learn about that in Physics 163. In fact, we'll be talking about interferometers as an example there. But so people did very accurate experiments trying to figure out, okay, is the speed of light really constant? And the answer is yes. No matter how you're moving, the speed of light you measure is the same. The value of those two things is the same. But how can this be? Well, the only way it can be is, again, if the transformation from one frame to the other isn't quite as simple as it seems. And people knew how to transform those, how to transform between reference frames. Like, what is my velocity here? What velocity does it turn into when I'm going to a different frame of rest, a different coordinate system that's moving? And those transformations are called the Lorentz transformations. They were known since the 1890s. Put a question mark here. They were known, but not very well understood. So they were named after Lorentz. Known, but not really understood. So people were like, look, mathematically, this way to go from one frame to the other makes sense. But it was only then in 1905 that Einstein published a bunch of stuff in 1905. It was the famous year when he had like 5 major papers. one of which got him the Nobel Prize later, but each of those 5 could have given him the Nobel Prize. One of those papers, not the one that got the Nobel Prize, but another one, was on the theory of special relativity. Special relativity really explained what those were, explained how to make sense of the fact that the speed of light is the same in all frames, that those values are the same no matter how you're moving, that the electric field and magnetic field sort of transform into each other and so on. So this whole culmination, these whole mysteries about electromagnetism, they were created by Maxwell's theory in the, I think, 1870s. Then for 30 or so years, confusion reigned. Lots of experiments trying to figure out, is this really the same? And then finally in 1905, Einstein published his theory of special relativity, and it immediately caught on. I mean, the history again is interesting, the little tidbits here and there. I'm not going to go into those now. There's a really good book I'm going to recommend here by Harvey Brown called Physical Relativity, which contains a lot of the history and the philosophy and some deeper thinking about what the theory actually says, how it makes sense of all of those concepts. So it's a fun read. It's technical to some extent, but it is fairly readable. So you might get lost here or there, but overall I think you'll get the gist of what's going on. So a fun little book to read maybe over the summer. Now again, I don't expect that you're able to reproduce, right, any of the stuff that I talked about. But I hope you got the basic idea of how do Maxwell's equations, well, first of all, how must we complete them with the displacement current? How are there mysteries regarding electric and magnetic field and dependence on the velocity when it comes to going to different reference frames on trains or not on trains? How do Maxwell's equations lead to the existence of light, right? Of radio, not radio waves, true, but electromagnetic waves more generally. So there is a whole course, right, worth of material here. Whole course in relativity we could take to actually make sense of that. But hopefully you have a bit of a feel for essentially what you've been learning, right? You've learned the 19th century electromagnetism. What happened next? There are mysteries here, right? We know now how to resolve them, but that'll take us into the 20th century, which then throws up, it's a terrible term, it creates new mysteries, and physics has been progressing from there ever since. Alright, that's it. That is it for Physics 162. I hope you had fun. I hope you find this stuff interesting. I hope your cup of coffee lasted you through all of this. And then hopefully I will see you at the final exam.